Hi. So in this video, we're going to start off by looking at simple harmonic motion, and we're going to be doing a few past paper questions, right? So we'll be doing two past paper questions in this video, okay? Now, in this case, the main idea is that we're going to start off by understanding simple harmonic motion. Look at the definition of the amplitude, as you can see, right? And then after that, we'll understand about damping, and with along with damping, we're going to be finding the period of the given oscillation. Okay. Now, first of all, we'll look at what amplitude means. So the main idea is that the amplitude is just defined as the maximum displacement from the mean position. Okay. So when we say over here, we'll say that in this case, if we write it over here, then the amplitude is the maximum position. In this case, the amplitude, right? Just the amplitude is nothing more than the maximum. The amplitude is the maximum displacement from the mean position. Okay. So it's the maximum displacement from your given mean position. So if you look at it in terms of our simple pendulum, then we know that for the pendulum, you're going to have the equilibrium position at the center. This is the equilibrium, and then the maximum displacement from this equilibrium position is going to give you your amplitudes, which is over here. Okay, so amplitude is the maximum displacement from the mean position. Now, for part 2, they're saying describe what is meant by damping, right? So we can sort of look at damping in terms of a mass spring system. So let's say that, I've got a mass spring system which is attached to the floor, and I've got the spring over here, and then down here I have attached a mass, okay? Now let's say I draw an axis. So this is the displacement axis, and then let's say that this is the time axis, right? So when we were looking at the concept questions, we were saying that what's going to happen is that this mass is going to go up and down like that, okay? And actually, to make this better, I'm going to draw the time over here, okay? So let's say in this case, if I have this mass spring system, let's say that, if I have this mass spring system, right? Let's say that this is your normal height. So this is your equilibrium position for this mass spring system. Okay, so this is equilibrium. Now, as we can see over here, for this given mass spring system, it's going to oscillate up and down. So it's going to go up to its maximum displacement. So this is maximum displacement. Then it will go to its minimum displacement, and it will keep oscillating up and down like this, right? So it's going to go up and down continuously. Okay. So normally when you had undamped simple harmonic motion, you would see that it would go to the maximum displacement. So this displacement would just be your amplitude. Then it would go back to the equilibrium position. So this is, as we can see, this is the equilibrium position. Then it would go to the minimum amplitude, and then it would go back to the time period. Okay. So I can actually even, I can make this a bit smaller. So it would sort of be like this. Okay. So you will find that all of these heights are the same. This is your maximum displacement, and this height comes up to be your amplitude. Okay, so this is your positive amplitude. Similarly, all of these heights are also the same, and so this comes up to be your negative amplitude. And so that's how we were seeing how displacement is varying with time. So normally we were saying that during simple harmonic motion, the object just goes up, then it goes down. So it starts at equilibrium, goes to the maximum position, then goes down to the minimum, back to equilibrium. And we said that, if you add a time variable, then along with going up and down, it will go to the right. So you get this sort of curved picture. Okay, so the object is continuously going up and down, up and down, up and down, and you're adding time. So this is how the object is functioning. Okay, so this is how the object would end up functioning. Now when you have this thing over here, this is a simple harmonic motion. So in simple harmonic motion, we would end up saying that the period and the amplitude would stay constant, right? This is what we define as simple, that is one of the things in simple harmonic motion, that the period and the amplitude of the oscillation will stay constant. Okay? But what happens in damping is that you sort of introduce a friction coefficient, right? So because there is friction, what's happening is that over time, the system is losing energy. Okay? So because the system loses energy, in the first complete period, you have a very high displacement. So I have just drawn the first period over here. Okay? This is the first complete period. And after this, in the second period, because the function, because the mass spring system loses energy, the system loses energy, and so because of that, the amplitude becomes smaller. Okay, and then it starts becoming smaller and smaller. Okay, so it's sort of like with each successive oscillation, right, the amplitude is falling. Okay, and the reason the amplitude is falling is because energy is being lost from system. Okay, and the reason the energy is being lost from system can come from the loss of energy, which in this case, can come from friction, perhaps. Okay, so therefore damping is shown as a scenario where the amplitude of oscillations, and this oscillations correlates to total energy. Okay, so the amplitude of oscillations / total energy of oscillations decreases with time. Okay, and this is because there is a force. So there is a force that opposes the direction of motion. Okay, so there's a force that opposes the direction of motion, and you can think of this as any sort of friction force. Okay, so damping is when the oscillations, so when the amplitude of oscillations decrease with time. So this is that when the amplitude of oscillations decrease with time, and this is because the total energy, this is because there is a force that opposes the direction of motion. Okay, so once again, the amplitude of oscillation / total energy of oscillation decreases with time, and it's because there is a friction force or any force that opposes the direction of motion. And we have seen the graph for damping over here. So as we can see, with each oscillation, each successive maxima is falling down, and then each successive minima also starts falling down. Okay, and you can actually see you can see damping in real life. I'm sure you would have seen a pendulum or some sort of oscillating object in real life. So you might have had a ball on a string, and you might have taken the ball on one side, and then you would have released it, right? And what you would have seen is that over time, the amplitude of the oscillations would have become smaller and smaller. So for example, first the ball could have gone at a very high distance, then the amplitude would slowly start to become smaller and smaller until the ball would ultimately rest. Okay, so you would have a decrease in amplitude, right? And that's because of real life friction. So if you're considering a real life pendulum, then the force that is opposing the motion of this ball would be coming from air resistance, okay, which is going to resist the motion of the ball. And that is why with each successive oscillation, the period of the amplitude of the oscillation will come down, and eventually the ball will come to rest. Okay, so that's for part one, and this is the basic idea for amplitude. Okay, now I'm going to be erasing all this, and if you want to copy it down, then you can rewind the video and sort of pause it and copy all this down. Okay, all right, so now that we're done with parts 1 and 2. Now that we're done with part A and part B, part 1, we can look at part 2. So in part so just to summarize damping, what this means is that the amplitude is going to fall, and it falls because of a friction force. Okay, now let's look at part 2. So the displacement of a liquid surface from its equilibrium position is x, and the acceleration a of the liquid in the tube is given by this following expression. Okay, so g is the acceleration of free fall, so we can assume this to be negative 9.81 meter per second squared, and L is the total length in the liquid column. So in this case, the total length of the liquid column, L, is 0.32 meters, and they're asking us to determine the period of the oscillation. Okay, so the way we can think about it is that we know that the defining equation for simple harmonic motion is A is negative omega squared x, and they give us another equation over here that A is negative 2g by L times x. So as we can see, if we put 2 and 2 together, we can say that omega squared is equal to 2g by L, and thus you would simply end up getting that omega is square root of 2g by L. And over here you can say that omega, which is your angular velocity, is going to be the change in theta over change in time, which just becomes 2 pi divided by the time period t. Okay, and this becomes the square root of 2g by L, right? And once we get all of this together, they're asking us to determine the period of the oscillation. So we have to find time t. So if we solve this equation, we get that 2 pi by t is equal to square root of 2g by L, which is the square root of 2g by the square root of L. So therefore 2 pi, this is square root of 2g by square root of L. So this is 2 pi root L by the square root of 2g multiplied by t is equal to 1. Okay, so you're just doing cross multiplication, and in this case you can take the t upstairs, so you can get that 2 pi times the square root of L by 2g. Okay, this becomes t. Okay, so this is what you get. All right, now the main thing over here is we know L to be 0.32, and we'll take the absolute value of gravity. Okay, because in this case you take the absolute value, right? If we take negative 9.81, then the equation won't work, because you can't have the square root of a negative value unless you use complex numbers, and we're not going to be doing that. Complex numbers, is like square root of negative 1, which you call as I, and I don't think that that's not going to be something you need to look at in high school, at least, unless you're doing HL maths or something related to that, right? Now in this case, 2 pi square root of L by 2g is equal to t. So this is 2 pi times the square root of L. So L we found was 0.32 meters, and then 2g is 2.2 times 9.81, and this gives you the time period. And then if you solve for this, then this simply ends up becoming 0.8 meter per second. Okay, so that is how we can look at these things. All right. Okay, so this is for question 1, as we can see, right? And then after this, we can move forward. Okay. So now let's look at question 2 over here. So in question 2, this is a question about simple harmonic motion. The graph shows the variation with time t, the acceleration of an object undergoing simple harmonic motion. So the first question is very important to describe simple harmonic motion. And in this case, this question comes a lot of times, so you should definitely know this, right? It's a easy question. You can always just remember the mark scheme, right? So as we have learned, for simple harmonic motion, the defining equation is acceleration is negative omega squared x. So therefore, the first condition of simple harmonic motion is that the acceleration, right? The acceleration is proportional. Okay, so the acceleration, and in this case, this is proportional to the displacement / distance. So it's proportional to the displacement / distance from the equilibrium / mean position. Okay. And one thing to note is that acceleration is proportional to displacement and it is opposite to displacement. Okay. Because the acceleration is proportional to negative x. So in one hand, acceleration is proportional to displacement, but you also have a negative sign, so you get the opposition. You get opposite sign. So acceleration is proportional to the displacement / distance. It's proportional and opposite to the displacement / distance from the equilibrium / mean position. Okay. Now let's look at part B, where it is saying that x has a mass of 0.28 grams. So calculate the maximum force that is acting on x. Okay. So the main idea for this is you simply just say force is mass times acceleration. And because you want to find the maximum force, you find the point with the maximum acceleration. And then you just do 0.28 multiplied by that. Okay. So in this case, the maximum acceleration in this graph comes over here. So if you look at this point, this comes out to be 2.6 meter per second squared. Okay. So the maximum acceleration we find is 2.6 meter per second squared. And the maximum mass they give us is 0.28 kilograms. So now we just do a simple multiplication. Okay. So if we do a simple multiplication, then the answer, in this case, 0.28 times 2.6 comes out to be 0.728 newtons, which is about 0.73 newtons, and that's the correct answer. Okay. Now for C, they're saying determine the maximum displacement of x and give your answers. So they're saying find the maximum displacement of x, and they're saying give the answers in terms of the appropriate number of significant figures. Okay. So what we can see is that over here we have this graph over here where acceleration is varying with time, right? Okay. So in this case, we can see how to go about this, right? So determine the maximum displacement of x, okay? So we know the acceleration time graph, right? And we know that the acceleration is negative omega squared x, okay? All right. So the way we can see it is that the acceleration is negative omega squared x, right? And what we can also find, right, is that in this case, if you have a simple pendulum, which is a simple pendulum over here, okay, then this is how the simple pendulum would be working, right? Okay. So we know that the maximum displacement happens at the amplitude positions. Okay? So the maximum displacement, which is what they're asking us to find, is going to happen at the amplitude. And because we want to find the maximum displacement, we want to find positive x, which is why it will happen at this amplitude. Okay? So it's going to so we are looking at the positive amplitude, a positive, right? Now, when we are looking at the positive amplitude, we know that in this case, the acceleration at this positive amplitude is going to be minimum. Okay? And that's because if this angle is theta, then the acceleration is negative g sine of positive theta, and that's why you get the minimum value of acceleration at your maximum amplitude. So that's why you can say acceleration is proportional to negative x, because at our max amplitude, we can clearly see that, at our max amplitude, we can clearly see that you have the maximum displacement in the x direction, but then you get the minimum acceleration. Okay? So in this case, they're asking us define the maximum displacement of x. Okay? So what we can say over here is that the acceleration is negative omega squared x. So we can say that if you have maximum x, then you have the minimum acceleration. Okay? And in this case, omega squared is just going to be a constant. Right? Okay. And so the way we can think about it, right, is like this. Okay, so the minimum acceleration, right, divided by negative omega squared gives us the maximum displacement. So we can say that the acceleration, right, is, and in this case we know that the omega is simply delta theta by delta t, which becomes 2 pi divided by the time period. Okay? That's what omega ends up becoming. Now we need to find the time period, which we can simply get from the graph. Okay? So if you look at the time period, then this is how the oscillation is happening, right? So this is one period t, and after that the function after that the function will start repeating itself. Okay, so that's precisely why you need to calculate this to be your time period. Okay, and what we see is that if you would look over here, then the time period t will come out to be 7.9 seconds. So that's the period for one oscillation. Okay, so therefore omega is 2 pi divided by 7.9 seconds. And this is all in SI units, so we are good, right? So radians is also good. Okay, so now we simply put it in the calculator, right? So if you do 2 pi, okay, if you do 2 pi divided by 7.9, you get omega to come up to be 0.794 radian per seconds. Okay, now so basically once you get this value for omega, then you can simply just substitute it, right? And we clearly find that the acceleration we need to use is the minimum acceleration. So if we just go in this acceleration time graph, we can simply find our minimum acceleration. So let's pick up this value. This becomes our minimum acceleration. And so our minimum acceleration is negative 2.6. Okay? So therefore you get that in this case, negative 2.6 is equal to negative, right? It's equal to negative times 0.794 squared, right? Multiplied by the maximum displacement. Okay? And if you just put it on the calculator, okay? So if you put this on the calculator, then let's go about solving it. Okay? So in this case, the answer we get is around 4. If you solve for the maximum value or the maximum displacement x, you get roughly about 4.12 meters. Okay? And they're saying that the answer for this, the maximum displacement, is going to be roughly around 4.11 meters. So it's roughly the same. Okay? Now the main thing to see over here, right, when you look at these when you look at the displacement, is that if you look at it in terms of the pendulum motion, you find that the maximum displacement is just your positive amplitude. So because your maximum displacement is just the positive amplitude, you can call it as the maximum displacement, or you can call it as positive x naught, where x naught is the positive amplitude. Okay? So that's the main idea for this. Now the tips for solving this is you need to be very good with those equations and the manipulations, that the acceleration is negative omega squared x, omega is 2 pi by t. Then in this case you need to know that the acceleration is negative k by m times x. You need to also understand that when you have an acceleration displacement graph, then you get this inverted line where in this case acceleration is proportional to negative x. And you need to know that the gradient of this is just negative omega squared. Okay? So, and then you need to be able to visualize. So you need to be able to visualize and understand the simple pendulum. Right? Okay? And the main thing for these questions is this question over here to define simple harmonic motion tends to be fairly common. So if you if you spend time on those, then that would be a good idea. Okay? Now, oh yes, also there's a part D, so we can look at how to solve this part. Okay? So let's look at part D over here. Okay? Part D is that a second object y is oscillating with the same frequency as x, but a phase difference of pi by 4. Sketch by the graph opposite how the acceleration of the object is going to vary with t. Okay? Now, in this case, what you can see is that so what I'll do is that I'm going to erase this part and we can write it again, right? So now we can look at D. Okay, so in this case they're testing you for phase difference. Okay, so first of all they're saying that the frequency is the same. Okay, the frequency is the same, but there's a phase difference. So they're saying, how does the acceleration of object y vary with t? Okay. So first thing you need to know is that the time period is equal to 2 pi square root of m by k. So this is for a mass spring system, and a mass spring system is a perfect example of simple harmonic motion. And if t is 2 pi square root of m by k, then what you simply get this is 2 pi square root of k by m. Actually, so this is 2 pi square root of m by k. Okay. Now, the main idea that you're going to be seeing over here is that if t is equal to the 2 pi square root of m by k, okay, then what we know is that the time period is 1 by frequency, which is 2 pi square root of m by k, and therefore what you can see is that the friction F is just equal to 1 divided by 2 pi square root of k by m. Okay, so the basic idea is that the friction is equal to 1 divided by 2 pi square root of m by k. Okay, and then if you sort of invert this, then this would simply become 1 divided by 2 pi square root of k by m. Okay, so the main point of this is that the frequency only depends on the main point of this is that the frequency in a mass spring system only depends on the spring constant and the actual mass. So therefore there is no relationship between frequency and acceleration. Okay, so the frequency does not depend on the acceleration, and the acceleration does not depend on the frequency, right? Okay, so that's the first part that you can see over here, right? Okay, so now what we can simply end up doing is that we can show the graph with phase difference. Okay, so when we look at phase difference, we just remember this formula over here. So we know that the formula for the phase angle is equal to the time difference. So this is the time difference, and this time difference is in seconds, divided by the time period multiplied by 360 degrees. Okay, so this is put in the concept videos, and I explain how you get this formula, and I have I talk about the intuition for how this formula works. Okay, now in this case, what we can see is that there is a phase difference of pi by 4, right? And so what we're given over here is that we are given a function which has a time t. Okay, but instead of a phase difference, instead of a difference in terms of time, we are given a difference in terms of angle. Okay, so we have to somehow convert this difference in terms of angle to a difference in time. So we just simply substitute over here. So they've given us the phase angle, which is pi by 4. Okay, so we just substitute the phase angle as it is, because that's what they've given it to us. And then we don't know the time difference, so we'll just call this small t. We do know in this case, we do know our time period. So the time period we calculated in the previous question, which is 7.9. And we're simply just multiplying this by 360. But because our phase difference is in terms of pi, we are going to be using 2 pi. Okay? So therefore, the time difference is pi times 7.9 divided by 4 times 2 pi. And so the time difference becomes 7.9 over here divided by 8. Okay, so that's what we get. The time difference becomes the time difference over here becomes 7.9 divided by 8. Okay, so we went from a phase difference of pi by 4 radians, and we converted it to a time difference of roughly about 1 second. Okay, so in the mark scheme they show this to be roughly around 1 second. So we are just going to be using 1 second instead of some complicated value over here, right? So we go back to the system over here, and what we see is that if this is our function, so this function is of the form of negative sine theta, right? So I've explained this, sort of recognizing these functions. So the way I did it was that this blue function looks at sine of theta, and then if you just reflect the sine of theta function on the x-axis, you just get negative sine of theta. Okay? So when you're dealing with simple harmonic motion, it helps if you have a simple idea of trigonometry, right? Now, in this case, we can start off by looking at how to draw these functions. So we know that the time difference is going to be 1. So over here, if the amplitude is at 2 seconds, we can draw an amplitude at 1 second. That's the time difference. And over here, if the amplitude is at 6 seconds, we can draw an amplitude at 5 seconds. So we are drawing one of these functions to be 1 second back. Okay? All right. Similarly, if the amplitude over here is at 10 seconds, we can draw one to be at 9 seconds. Okay? So we get different pointers for where our function should be over time. And similarly, if this function is crossing here at 4 seconds, it can cross at 3 seconds. So you're showing a lag of 1 second. Similarly, if it's crossing at 8 seconds, you can show this to be 7 seconds. Okay? And if this is crossing at 12 seconds, you can show this to be 11 seconds. Right? And so once you get all of this listed down, then you can sort of draw an approximate graph like this. Okay? So what you have to note is that all of these functions, both of these functions are exactly the same. Okay? But the only difference is that they're shifted by 1 second to the left. Okay? Now, if you want, you can draw a function that is shifted 1 second to the right. So that's your personal choice, whichever function you can feel like, right? But the main idea is that this new function should be shifted by 1 second. Okay? All right? So that's how we would be looking at this idea of phase difference. All right? So this is the main idea. And we looked at the phase difference formula, which you should know. All right? Okay? So this is the main idea for this thing. And the phase difference formula, you can just remember it to be, it's just a ratio. You're taking the ratio of the time difference and you're dividing it by the time period, and then you're multiplying it by 360 or 2 pi, right? So just think of it, I explained this in the concept video as well. You can think of this in terms of like sector area. So let's say that if this sector area is, if this sector angle is 120 degrees, and we want to find this area, and let's say if the radius of the circle is 10, then you would have learned that the area of this sector is, in this case, it's just going to be theta divided by 360 times pi r squared. So this would be 120 divided by 360 times pi r squared, which is 1/3 times pi r squared. And this makes sense because the shaded area looks to be 1/3 of a circle, which is why the area is 1/3 pi r squared. Okay? So in this case, we took an angle theta, we divided it by 360, and then we multiplied it by pi r squared. So we sort of took a ratio. Okay? We took a ratio. And that's exactly how the phase difference works. It's just a ratio. It sounds complicated, but it's a simple ratio that you're taking. And in a phase difference, you can translate a phase difference to a time difference, or you can go from a time difference to a phase difference. And so the ratio goes along the overall goes at the, first of all, it goes at the overall time period, and it also looks at the overall angular displacement or the overall angular movement, which is 360 degrees. Okay, so you're taking the ratio and then you're converting it from angle to time or time to angle, and like that. Okay, so with this we are done with 2 questions of SHM. We are done so we have covered quite a few topics, right? And we have looked at paper 2 questions for SHM. Okay, all right, good luck.